When sizing service entrance conductors, it is important to consult the National Electrical Code, specifically Tables 310.16 and 310.15.6. These tables provide guidance on the allowable ampacities of conductors based on their insulation type, size, and installation conditions. Table 310.16 lists the ampacities of insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius, in free air and installed in raceways or cables. Table 310.15.6 provides specific ampacity adjustment factors for dwelling units. For a 100 amp service, if using 75 degrees Celsius THWN copper conductors as referenced in the 1999 NEC, Table 310.16 indicates that a #3 copper conductor is suitable. Similarly, Table 310.15.6 would also specify a #3 copper conductor for a 100 amp service in a dwelling unit. For a 200 amp service, Table 310.16 indicates that a 3/0 copper conductor is required. However, Table 310.15.6 allows the use of a 2/0 copper conductor for a 200 amp service in a dwelling unit. The neutral conductor sizing is addressed in Table 250.66 of the National Electrical Code. This table provides the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. For a 100 amp service, the neutral conductor should be sized at 100% of the phase conductor size, which in this case would be a #3 copper conductor. For a 200 amp service, the neutral conductor should also be sized at 100% of the phase conductor size, resulting in a 3/0 copper conductor. Equipment grounding conductor sizing is specified in Table 250.122 of the National Electrical Code. This table determines the minimum size of the equipment grounding conductor based on the rating of the overcurrent protective device in the circuit. For a 100 amp service, the equipment grounding conductor should be sized at 25% of the phase conductor size, requiring an #8 copper conductor. For a 200 amp service, the equipment grounding conductor should also be sized at 25% of the phase conductor size, resulting in a #6 copper conductor. It's crucial to remember that these are minimum sizes, and local codes or specific installation requirements may necessitate larger conductors. Always consult the latest edition of the National Electrical Code and local regulations for accurate and up-to-date information. Selecting the correct size of electrical conductors and grounding is critical for the safe and efficient operation of electrical systems. Undersized conductors can overheat, leading to insulation breakdown, potential fire hazards, and voltage drop, which can negatively impact the performance of connected equipment. Properly sized conductors ensure that the electrical system can handle the intended load without exceeding its capacity or compromising safety. In addition to conductor sizing, grounding plays a vital role in electrical safety. Grounding provides a low-impedance path for fault currents to return to the source, allowing overcurrent protective devices like circuit breakers or fuses to quickly trip and disconnect the faulty circuit. This minimizes the risk of electrical shock and prevents damage to equipment. The equipment grounding conductor connects the non-current carrying metal parts of electrical equipment to the grounding system, ensuring that any fault current is safely conducted back to the source. The grounding electrode conductor connects the grounding system to a grounding electrode, such as a ground rod or water pipe, providing a direct connection to earth. This connection helps to stabilize the voltage to earth and provides an additional path for fault currents. When working with electrical systems, always prioritize safety. To energize circuits before working on them, use appropriate personal protective equipment, and follow all applicable codes and regulations. If you are not comfortable working with electricity, consult a qualified electrician. Firstly, consider the continuous load. The National Electrical Code requires that conductors be sized to carry not less than 125% of the continuous load. A continuous load is defined as a load that operates for 3 hours or more. For example, if a circuit supplies a continuous load of 80 amps, the conductors must be sized to carry at least 100 amps. 80 amps x 1.25 equals 100 amps. Secondly, determine the appropriate ampacity of the conductors. The ampacity of a conductor is the maximum current it can carry continuously without exceeding its temperature rating. Table 310.16 in the National Electrical Code provides the ampacities of various conductors based on their insulation type, size, and installation conditions. Select a conductor size that has an ampacity equal to or greater than the calculated load. Thirdly, consider voltage drop. Voltage drop is the reduction in voltage that occurs as electricity flows through a conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To calculate voltage drop, you will need to know the length of the circuit, the current flowing through the circuit, and the conductor's resistance. Use a voltage drop calculator or consult the National Electrical Code for guidance on calculating voltage drop. Fourthly, select the appropriate insulation type. The insulation type of a conductor must be suitable for the environment in which it will be installed. Consider factors such as temperature, moisture, and exposure to chemicals. Common insulation types include THHN, THWN, and XHHW. Refer to the National Electrical Code for guidance on selecting the appropriate insulation type for your application. Fifthly, consider the number of conductors in a raceway or cable. When multiple conductors are installed in a raceway or cable, the ampacity of each conductor must be derated to account for the heat generated by the other conductors. The National Electrical Code provides derating factors based on the number of conductors in a raceway or cable. Be sure to apply these derating factors when sizing conductors. Sixthly, select the appropriate overcurrent protection. Overcurrent protection devices, such as circuit breakers or fuses, are designed to protect conductors from overloads and short circuits. The overcurrent protection device must be sized to protect the smallest conductor in the circuit. The National Electrical Code provides guidance on selecting the appropriate overcurrent protection device for your application. Seventh, consider the ambient temperature. The ambient temperature is the temperature of the air surrounding the conductors. If the ambient temperature is higher than the temperature rating of the conductor, the ampacity of the conductor must be derated. The National Electrical Code provides derating factors based on the ambient temperature. Eighth, consider the type of load. The type of load can also affect the conductor size. For example, motors and other inductive loads require larger conductors to handle the inrush current that occurs when they start. The National Electrical Code provides guidance on sizing conductors for different types of loads. Ninth, consult with a qualified electrician. If you are not comfortable sizing conductors yourself, consult with a qualified electrician. A qualified electrician can help you determine the appropriate conductor size for your application and ensure that the electrical system is safe and compliant with the National Electrical Code. 10th, review local codes and regulations. Local codes and regulations may have additional requirements for conductor sizing. Be sure to review local codes and regulations before starting any electrical work. By following these steps, you can ensure that you select the correct size of electrical conductors for your application. Remember to always prioritize safety and consult with a qualified electrician if you have any questions. Grounding electrode conductor sizing is crucial for safety. Table 250.66 in the National Electrical Code provides guidance on this topic. This table outlines the minimum size requirements for grounding electrode conductors based on the size of the service entrance conductors. The grounding electrode conductor connects the grounding electrode to the electrical system's grounded conductor, typically the neutral. The size of this conductor is essential for providing a low impedance path for fault currents, ensuring that overcurrent protection devices operate effectively in the event of a ground fault. Selecting the correct size grounding electrode conductor is paramount for personnel safety and equipment protection. When sizing the grounding electrode conductor, firstly, determine the size of the service entrance conductors. This is the primary factor that influences the size of the grounding electrode conductor. Refer to the National Electrical Code Article 250 for the specific requirements. Secondly, consult Table 250.66 in the National Electrical Code. This table provides a direct correlation between the size of the service entrance conductors and the minimum size of the grounding electrode conductor required. Thirdly, ensure compliance with local amendments. Local jurisdictions may have amendments or additions to the National Electrical Code that could impact the sizing requirements. Always check with the local authorities to confirm any specific rules in your area. Fourthly, consider the material of the grounding electrode conductor. The table provides minimum sizes for copper, aluminum, and copper-clad aluminum conductors. Choose the appropriate column based on the material you intend to use. Fifthly, account for multiple grounding electrodes. If multiple grounding electrodes are used, the grounding electrode conductor must be sized to accommodate the combined capacity of all electrodes. Refer to the National Electrical Code for specific guidelines on sizing conductors for multiple electrodes. Sixthly, verify the conductor's ampacity. Ensure that the selected grounding electrode conductor has an ampacity rating sufficient to handle potential fault currents. The ampacity should meet or exceed the requirements outlined in the National Electrical Code. Seventh, consider the environmental conditions. Environmental factors such as corrosion and moisture can affect the long-term performance of the grounding electrode conductor. Choose a conductor material and installation method that can withstand the specific conditions at the installation site. Eighth, protect the conductor from physical damage. The grounding electrode conductor should be protected from physical damage to maintain its integrity. Consider using conduit or other protective measures in areas where the conductor may be exposed to mechanical stress. Ninth, properly terminate the conductor. Ensure that the grounding electrode conductor is properly terminated at both the grounding electrode and the electrical system's grounded conductor. Use appropriate connectors and follow the manufacturer's instructions for a secure and reliable connection. 10th, regularly inspect the grounding system. Periodically inspect the grounding system, including the grounding electrode conductor, to ensure that it is in good condition and functioning properly. Address any issues promptly to maintain the effectiveness of the grounding system. By following these guidelines, you can ensure that the grounding electrode conductor is properly sized and installed, providing a safe and effective grounding system for the electrical installation. Proper grounding is essential for protecting people and equipment from electrical hazards. Ignoring this critical aspect of electrical design can have serious consequences. Always consult with a qualified electrician or electrical engineer to ensure that your grounding system meets the requirements of the National Electrical Code and local regulations. The information provided here is for general guidance only and should not be considered a substitute for professional advice. Always prioritize safety and adhere to all applicable codes and standards when working with electrical systems.